Okay, so here we go. Let's have a look at this. All right. So Riley, what are we given here?
A spherical ball.
Okay, we're given a spherical ball, and they're telling us some stuff about this. Okay, so and really, let's read through the whole question first. We've got a spherical iron ball, 6 inches in diameter, is coated with a layer of ice of uniform thickness. If the ice melts at a rate of 11 cubic inches per minute, how fast is the thickness of the ice decreasing when it is 2 inches thick? How fast is the outer surface area of the ice? We've got two questions. How fast is the outer surface area of the ice decreasing? Okay. So we need to probably add some stuff to our picture, some variables. What should we probably do? Okay, we need the volume equation probably. Good. Okay. So we know that the volume equation, I'll put that down a little bit because that's going to probably be our parent equation, right? Yeah. Okay, so there's potentially our parent equation. Okay, so now what are our snapshot values? We're going to take one frame in the movie, the frame specified up here, and what stuff do we know? Somebody tell me something we know. Riley, you got to tell me something we know.
That it's 6 inches in diameter and it's moving it's melting at a rate of 11.
Okay, so but we got to label those things. What do we got here?
X dot is 11.
What is diameter?
Okay, there's too much chatter going on here. We got to really focus on this. So if the diameter of the spherical ball is 6 inches, then what does that mean? Okay, radius is 3. But now we got to be careful here. If the radius of the iron ball is 3, we're saying that this distance right there is not going to change, right? That's a constant, and it's 3 inches. Okay, yeah, now the other thing we know here is that, okay, plus x. So you're going to say x is maybe the thickness of the ice? Okay, if you think about this though, in terms of, we can do that. But if you think about this in terms of the parent equation, seen from the outside, now think about it, seen from the outside, it just looks like what? Okay, or x plus. But what does this object even look like from the outside?
Like a ball, right?
Just like a ball of ice, right?
Yeah.
Right? So sure, we could say that the radius of the whole thing is 3 plus x. We could do that, and then x is the thickness of the ice, right? Okay. Does it ever ask, though, for the thickness of the ice?
No.
Not really, right? It wants to know how fast the thickness is changing, right? And so that would be x dot, but is there another quantity that would be equal to x dot?
15.
R dot would, wouldn't it? Okay, right, now let's look at this. This is kind of important. So you could set this up as the this outer quantity being x, right? And then the radius of the whole thing is 3 plus x. That's going to work fine. But why not instead? Why not just call the radius of the whole thing r? Because wouldn't you agree that as the ice melts, x and r are going to be changing at the same rate, right? As the ice melts and the overall radius shrinks, let's just say hypothetically that the outer radius is changing at a rate of 1/10 of an inch per minute, that the radius of the whole thing. How fast would the thickness of the ice be changing then? Well, wouldn't it just be 1/10 of an inch per minute? Right? Because is the radius of the iron ball going to change? No. It's not going to change at all, right? So x plus 3 is just going to change, that quantity is only going to change as fast as x changes. Once all the ice is melted, it's not going to change anymore, right?
Yeah.
That's kind of important. You see that trick? this is a big trick that we use in physics and math a lot. If we can trade the rate of change of one quantity for the rate of change of an easier quantity, if they're equal, those rates of change are equal, why not do it, right? So rather than answer the question, what is x dot, let's instead answer the question, what is r dot? Because they're the same answer. Even though x and r are different, r dot and x dot are equal. The rates of change have to be the same. Agreed?
Yeah.
Okay, so that makes this problem a little bit easier. Not a ton, but a little bit. Okay, so then if we're going to do that, what are those values? So we need to know our snapshot value probably of r. What is that then?
3.
Of
For
r.
the whole, no.
Yeah, so and what's x for our snapshot? 2, so therefore r is 5. Okay, and the units are inches. We'll leave the units out of our calculations. Okay, so that's one thing we know. They give us something else too, another quantity.
The 11.
The 11. Yeah, let's look at this. Okay, that's a v dot. How'd you know that? Okay, because we've got units of volume over units of time, right? So that must be change in volume over change in time, right? So that's a rate of change of volume, isn't it? So that's v dot. Now, the ice is melting, so what is that telling you?
Minus.
It's negative, right? The volume is decreasing, so the rate of change is negative, right? What are we trying to find? At least for part A?
Thickness of the ice minus 2 inches. How fast is decreasing?
Okay, how fast is decreasing? Good. So what quantity is that? Okay, x dot, but we don't really want an x. We don't have x's in here. R dot, right?
But you said 11 was negative, no?
Oh, it is. You're right. Whoops, it's negative. Yep. Good.
Well, thank you.
Okay, so now we were already, the parent equation we already got, right? If we want to find the equation, if I ignore the dots, we want to find the equation that relates V and R. Well, this is a sphere, so that's just the volume of a sphere, which is that, right?
Yeah.
Okay, so now we got to move on to step 3, which is we have to implicitly differentiate with respect to t, so we get our rates out of the parent equation. So what do we get? Equals. Yeah, that's just a constant, right?
Yeah.
So 4 pi r squared r dot. Good. Okay. And we're just trying to find r dot, so all we really need to do is just isolate r dot, right? So we'll divide both sides through by 4 pi r squared. And so we get r dot equals v dot over 4 pi r squared. And if we plug and chug, then we get negative 11 over 4 pi times 5 squared.
Yeah.
Right? Okay, we'll just leave the units off. Our units are going to be, length is going to be inches, time is going to be meters, right?
Yeah.
Okay, and so what do we get if we do that? So, let's see, we want it, oh, that's a good question. I think on there it says round to, I don't remember.
It's a fraction. So it says a fraction.
It's a fraction? Okay, we want it as a fraction.
No, it's negative 0.035.
Okay, so,
That's right.
okay, so if this is asking for a fraction, this is asking for a fraction, this is just going to be, our answer is negative 11. Okay, and the units would just be what?
Inches per minute. Squared inches per minute.
Well, hold it, it's r dot, so it's a rate of change of radius. So what is it, Alexis? Inches per minute, because we're going to have, what would the rate of change of radius be? Radius is measured in inches in this problem.
Oh, yeah.
Over the unit of time would be minutes, right?
Yeah. So that's our answer?
Okay, but we got to be a little careful. We have to interpret this answer now. And if we interpret this answer, it says, how fast is the thickness of the ice decreasing?
-0.
So we ignore the negative.
Because it already says decrease.
Okay, stop talking. We ignore the negative because it already told us that it's getting smaller. It says, how fast is it getting smaller, in other words? Is it decreasing, right? So we just want the magnitude, and that's gonna be that. If they want it as a decimal, obviously just put it in your calculator. No big
So
deal.
would it mark it as wrong if we put it in a negative?
Yeah.
Yeah, it would.
Wow.
Okay, so then for part B, I won't even necessarily go through all of part B. It's not that, once you do part A, that one's pretty simple. By the way, I rewrote all these questions so they give you the formulas. Not that you probably needed them, but I did that. So for part B, we're asked for the rate of change of surface area. So what's our parent equation gonna be there? Okay, good. So S equals 4 pi r squared. So what do I have to do then? Differentiate, and I get, okay, but,
S dot
good.
equals
S dot equals,
8 pi r
okay, and look what we could do here. We really answered this question in part A, didn't we? So whatever answer we got, we're just gonna plug that in for r dot, and now we can plug and chug with other quantities, right? And we're done.
I understand that.
Would we include the negative in the R dot on this side?
Okay, good question. Now, Julie asked a good question. Do we want to include the negative sign? Yeah, we do, because r dot is negative. However, once again, if you interpret the question, that's gonna make this S dot negative, which it should be, right? Because obviously the surface area is decreasing as the ice melts and the whole thing gets smaller, right? But they ask, how fast is the outer surface area of ice decreasing? So we don't include the negative in our answer.
Okay, yeah.
Right.
Same thing as the earlier.
Yep.
So the earlier question would also be negative.
Well, it would, but we're gonna make it positive in our answer because they were asking us how fast is it decreasing.
So you would put the negative in that part?
You would here, sure.
You would have a negative.
You get a negative answer, but then you enter a positive number. Okay. How about this one? One very much like it. Okay, so they drew us a picture, but we could have, let's just for a second talk about why this is the right picture. An airplane is flying at an altitude of 6 miles, so that means that the height is constant, doesn't it?
Yeah.
So it's flying horizontally. It flies directly over a radar installation, or radar antenna, when the plane is 10 miles away. Okay, and look, they're telling us, so S equals 10. That's the distance away from the radar. The radar detects that the distance S is changing at a rate of 240 miles per hour. What's the speed of the plane? Okay, well, the plane is traveling horizontally, right?
Yeah.
And so let's, which quantity are we really looking for based on that drawing? X dot, good, right? How would you describe X? You know, probably as the horizontal distance that the plane has traveled, right? And that's really, it's traveling horizontally. So really what we want is the rate of change of the horizontal distance. Okay? That make sense? Okay? So then what are the snapshot values of our variables here? No. X isn't 10.
S.
Oh, you said S, all right.
What? I was like, wait, what?
Okay. What else do we know?
Wait, where'd you get the 6 from?
6 miles.
6
So
miles.
X
Oh, yeah,
is
yeah, yeah.
6. Y is 6.
Y is
X
Yeah, okay,
X.
y would be 6, but do we want to call it y?
No.
How come?
Why?
You don't want that variable.
Because we don't want that, it's not a variable, right? We don't want to confuse ourselves by implying that y is a variable. It's a constant, so let's just label it with its number, right?
Let's do it.
What else do we know?
It's traveling at a rate of 240 miles per hour.
Okay, well, the radar detects the distance. In other words, the distance from the radar to the plane is changing at a rate of 240 miles per hour.
S dot.
S dot, okay. And what are we looking for?
We're looking for X dot.
There we go. Okay, so what is our, do you suppose, is going to be our parent equation here? We want to relate x's and s's, probably Pythagorean theorem, right?
How is the X complete?
Everybody see that?
Yeah.
Okay, this is the hypotenuse, right? So we could say x squared plus what?
Y squared.
But we don't want to call it a y.
S squared.
Equals 10 squared.
No.
S squared.
S squared.
But
Right.
S is 10.
Right, but okay, but
No.
let's not, we can't plug that in because that's a snapshot value.
Oh, so it's not always 10, right?
Oh, but the dots. Wait, so do we isolate X?
Okay, so s is a variable that can change, right? But the 6 can't. So we're gonna plug in the value for, what we might have called y, because it's not a variable, but this is. Right now, think what would happen if we plugged in the 10 for s.
We get an X.
We'd get a specific x value,
And
right?
then we can't take the derivative.
Yeah, what would the value of x dot be then if x? It'd be 0. Well, obviously the plane is moving, right? Okay, so that would cause a mistake. So here's our parent equation, now what? Differentiate, good, so we're gonna find out that, what?
2x plus
0.
X dot.
Oh, what the?
Plus 0 equals,
2S dot.
okay, we could cancel the 2's to make things a little easier, right? And then algebraically, what's the one step we need to isolate x dot?
Divided by X.
Divide by x. So we get x dot equals s dot over x. Okay, we don't know x though, right? But that's okay.
But we can figure out X after that.
Good, we can figure out x, can't we? We really have two choices. We could either solve for x in terms of stuff that we do know and plug that in, right? Just do some algebra, just do substitution algebra. So we could say x equals the square root of s squared minus 36 and plug that in down here, right? If we did that, that would give us s dot over the square root of s squared minus 36. And now we could just plug and chug with the green equation. Or, what's our other option?
Can we just find the
Yeah, we could just add another snapshot value for x, right? We could also do this. We could say x equals, well, what? When s is 10, we're going to get 64. 100 minus 36, so we're going to get the square root of 64, which is 8. And then we could just plug that in right there, right?
Yes, we could.
Take your pick. It doesn't really matter. Let's do the first one. How about?
No.
So that's going to give us x dot equals s, which was 10, times s dot, which was 240, right? Divided by x, which was 8. And so that gives us 300.
Wait. Where did
Units are going to be what?
400.
Miles per hour.
Yes.
There's a difference.
Okay.
Stop.
Okay. Does that make sense?
It makes a lot of sense, actually.
Okay.
I'm understanding something. I'm sure we can.
All right. Last one. Last one, and then I'm done. Then you're on your own.
I heard this one.
So a particle moves along the parabola y equals x squared in the first quadrant in such a way that its x coordinate increases at a steady 30 meters per second, okay? How fast is the angle of inclination theta of the line joining the particle to the origin changing when x equals 3, okay? So what do we probably want to do here? I mean, we've got a particle, right, moving along this parabola. So let's draw the particle, right? So here's our particle, like an ant. So there's our particle. What are the coordinates of the particle? It's changing, isn't it? They're going to vary because it's moving, but what's the x coordinate going to be? Well, x, I guess, right? Okay, what's the y coordinate going to be? Y, true. But what's y equal to?
30 meters per second.
X squared, right? Okay, wouldn't we rather, now let's think about this, wouldn't we rather have one variable than two variables to deal with?
Yeah.
Right? So rather than calling this x and y, let's just call this x and x squared, right? Okay, I'll tell you what, let's do. That's fine, we can do that. Okay, so then we want to know the distance between those, which we can represent like that, right? There's D. And really then, well, let's go ahead and write in some snapshot values maybe.
Okay.
What's x equal to?
X equals
3, okay. And what else did they tell us?
y equals x squared.
True.
Or does that not work? Sorry.
Well, I mean, true, we already kind of did that. We said our coordinates x, y, we just replaced them with x,
And x.
x squared.
Okay.
Okay, but what are some other, we look for the numbers, right? The numbers in the equation are telling us snapshot values. X dot. Yeah, they're telling us that the x coordinate increases at a steady 30 meters per second. So, in other words,
X dot equals 30.
yeah, x dot equals 30. Good, now what are we trying to find? Okay, we're trying to find here the angle of inclination of the line joining the particle to the origin. Well, here's the line. So, that's our theta then. Angle of inclination, that probably needs to be defined. Angle of inclination just means the angle between the horizontal and whatever you're talking about, line in this case, right?
Correct.
So that's a specific math word, and it's just telling us that. Okay?
Oh, wait, that whole angle.
So how can we've got to come up with a parent equation then that relates, so we're trying to find theta dot, aren't we? Okay.
To be tangent theta equals x squared.
Okay, good. So we got to find a way to relate the x's and the thetas, right? Because we're going to ignore the dots, and so our parent equation has to be probably a SOHCAHTOA thing. And wouldn't it just be this, right? We'll just make a right triangle out of this, right? Now, what are the lengths of the sides of the right triangle? If the coordinates of this point are x squared, what's that tell us about the lengths of the sides of that triangle?
X is up.
Yeah, the base is x and the height is x squared, right?
Yeah, I agree.
Does that make sense? Okay, so then we want to come up with the easiest equation we can that's going to relate all those, which is probably a tangent, right? So then our parent equation becomes, and we can look at that and see if it really does look like that's going to be the best way. So tangent of theta equals opposite over adjacent. Well, that simplifies nicely, doesn't it? What's x squared over x? X. So our parent equation just becomes tangent theta equals x, right? Everybody with me?
Yeah.
So is you arctan it?
So, no. I mean, we don't really want to do that because for one thing, we will later, but for now, we do not have the derivative rules for any of the inverse trig functions, arc trig functions, right? So we can't, right, we can't solve for theta and then differentiate because we don't know the rule. Okay, but we do know the rule for tangent, so what do? And we just differentiate implicitly. We just differentiate that whole thing with respect to t. What's that give us on the left side?
Cosecant squared.
Hang on, derivative of tangent is
Secant squared.
secant squared. Okay,
Theta dot.
theta dot equals
One, X dot.
x dot. Okay, we're trying to solve for theta dot, right? So then we end up with theta dot equals x squared over secant squared.
X squared.
Secant.
Oh, sorry, x dot, not x squared, my mistake. X dot over secant squared x, which is kind of a dorky thing to do to the, oh, theta, yeah, sorry. Okay, but dividing by secant squared theta is kind of dumb. What should we do instead? Yeah, good. The reciprocal of secant is cosine, and so 1 over cosine would just be cosine, right? A secant on the bottom is equivalent to a cosine on the top, right? Say it again.
Can you write it all out?
Sure, sure. Well, that's what that's saying is 1 over secant theta would be the same thing as saying 1 over the reciprocal of cosine theta, right? Which is just equal to cosine theta, right?
Squared.
Okay, it is, you're right, so we'll square it. So in other words, this is just equal to x dot cosine squared theta, right? Okay, so let's go back up to our triangle and let's plug in some stuff, right? So if we know that cosine theta is the ratio, because now we're just gonna plug and chug, right?
Yeah.
So cosine is the ratio of adjacent over hypotenuse. So if we want to plug in the snapshot values for our triangle, they just look like, wasn't x 3?
Yeah.
So we get 3, and then this was
Over 9.
9. And so this is just going to be the square root of 90, right? So we just get 3 radical 10 if we just do the Pythagorean theorem, because it's a right triangle, right? Square root of 9 plus 81 is the square root of 90. Square root of 90 is just square root of 9 times square root of 10, so 3 radical 10. Okay? And you know what? Why not even just leave it? Being as we're going to square it, that's dumb of me to simplify it. Why not just leave it as an unsimplified radical? How come?
Because then you have a simple.
Right, because when I square it, I'm just going to undo the radical anyway. So I'd really probably just rather write this as the square root of 90, right? Everybody see that? It's kind of a minor thing, but it helps. So now we plug and chug. So what do we get? X dot was 30, right? So we're filling in there. 30 times the square root of, oh, so what did we get here? We got 3 over the square root of 90,
All squared, right?
all squared. So what's that going to be?
9 over 90, so.
So 1 over 10, right? And 30 over 10 is 3. So theta dot is 3 what? What are the units of theta dot going to be?
Yeah, I don't know the time, but what's the time?
Time, okay, let's look at the units.
Over second.
Seconds.
It's gonna be rad.
Meters.
Or, I mean, radians, not rad.
Okay,
Rads.
okay, yeah. Is it going to be radians or degrees? Okay, how come?
Because we didn't use degrees.
Yeah, because degrees are not a thing, right? Ask yourself the question, and this is kind of a good way to think about this. This will help. What if whoever, John Degree, whoever made the first degree, what if he had divided the circle up into 720 degrees instead of 360? That would now change here in the year 2016. That's somehow going to change your answer to a problem? That can't be, right? Whatever old John arbitrarily picked for the size of an angle, or size of a degree, should have no bearing on the answer to that question, right? But a radian, that's a real thing.
Yeah.
Yeah.
Who did invent the degree?
I don't know. Probably wasn't John Degree.
I mean, it's nice guess.
sense?
Yeah.
All right.
I think that's the first time we got
Wait.
here.
I know. Amazing. We're getting good.